Hello everyone, welcome back to Deterministic Optimization. Let's continue our discussion on algebraic aspect of linear optimization. So in the previous lectures, we learned how to find basic solution, how to find basic feasible solution for a standard form linear program. And the concept of basic solution and basic feasible solution is general. It doesn't have to be restricted to standard form linear program, but applied to all linear program. And we focused on standard form linear program because later we'll see that we'll develop algorithm to solve standard form linear program. It's just a more standard way to handle linear programming problem. So we focus a lot on basic solution, basic feasible solution, and you may have the question, why do we care so much about basic feasible solution? So in this lesson, we'll exactly discuss that, identify why basic feasible solution is important for linear programming problems, and recognize what is special about standard form LP regarding basic feasible solution. So the first question is, does every LP have a basic feasible solution? And the answer is not every linear program has basic feasible solution. Remember, a basic feasible solution is an extreme point in the geometric point of view. An extreme point is those corner points. So this statement says not every linear program has a corner point in the feasible region. So when we say not every linear program has a basic feasible solution, it means the feasible region of that linear program may not have a basic feasible solution. So the example is very simple. You just think about a line or a half space. Here's a line. This line is a polyhedron because it is an intersection of two half spaces. The half space to the right intersect with the half space to the left. Both half spaces include this line in the middle, so the intersection is exactly this line. So this satisfies the definition of polyhedron as intersection of finite number of half spaces. So a line is a polyhedron, and a polyhedron is what we're talking about, right? The feasible region of LP. So this polyhedron does not have any basic feasible solution. There's no corner point here. The same is true if you look at a half space, maybe one on the right. This half space here also does not have any basic feasible solution. So if you minimize a linear function over the half space, that LP does not have a basic feasible solution. So then the question is which LP has a basic feasible solution? Meaning which polyhedron has basic feasible solution, or which polyhedron has an extreme point? And the theorem is the following. The theorem says a polyhedron P has an extreme point if and only if P does not contain a line. Okay, so exactly rules out this example that we just gave. This is a polyhedron that contains a line because it's a line itself. And if you look at half space, it's a polyhedron. It also contains a line, for example, on the boundary here, or parallel to this inside the half space. So these two examples are polyhedrons that actually contain a line, right? So the theorem says that's the only case where a polyhedron does not have an extreme point. So all other cases, when the polyhedron does not contain a line, that polyhedron must have at least one basic feasible solution, equivalent at least one extreme point. Okay, so we can immediately apply this theorem to standard form problem. Remember, standard form LP is what? It's AX equals B and X non-negative. So if this polyhedron AX equals B and X non-negative is non-empty, has at least one point, then this polyhedron cannot contain a line. So why is that? Because the non-negativity constraint. X need to be greater than or equal to 0. So if assume there is a line in this standard form LP polyhedron, then because it's a line, so on that line, the point can go to positive infinity and also negative infinity. So it must become negative at some point. Therefore, it cannot happen if we have constraint that X is non-negative. So that means standard form LP's polyhedron does not contain a line. Therefore, it must have a basic feasible solution when it's non-empty. Of course, you could have a polyhedron that is empty, so there's no basic feasible solution. So for non-empty, that's why I call it feasible standard form LP. The feasible region is not empty, then it must have a basic feasible solution. So that is good because if we solve standard form LP, and it's feasible, then we guarantee to have a basic feasible solution. But if we solve a general LP, then we may not have a basic feasible solution. So why basic feasible solution is important? Because they are actually optimal solutions, or they contain optimal solution. So if an LP has a finite optimal solution, meaning it does not go to positive infinity or negative infinity, especially does not, if you minimize, does not go to negative infinity. If you maximize, does not go to positive infinity. Then, so that's what we call finite optimal. So if LP has a finite optimal solution, then a optimal solution is a basic feasible solution. So be careful with the way that I say it. I said an optimal solution is a basic feasible solution. I didn't say the optimal solution is a basic feasible solution because there may be multiple optimal solutions. Okay. So for example here, this is a polyhedron. Actually, it's a polytope, right? Because it's bounded as 6 extreme points or 6 basic feasible solutions. And if I minimize C transpose X in this direction, so along this direction, C transpose X increases. So to minimize, I need to go to the negative that direction. So if I go along that direction, I'll hit this basic feasible solution right here. So that is the optimal solution. So in this case, this LP minimize C transpose X over this polyhedron, this LP does have a unique optimal solution, and it is a basic feasible solution. Okay, so from this statement, you can immediately tell if the optimal solution is unique, then it has to be a basic feasible solution. But what if the solution, optimal solution, is not unique? So in the same example, same polyhedron, I can minimize a slightly different linear function, just slightly tilted from the previous one. And then when I minimize, I actually hit the entire edge here. Every point on this edge is an optimal solution. Okay, so then you see that it's not true that every optimal solution is a basic feasible solution because we only have 2 basic feasible solutions here that are optimal. But one of the optimal solutions is basic solution, for example, here or here. So that's why I carefully said an optimal solution is a basic feasible solution. Okay, so let's summarize the importance of basic feasible solution. First, because standard form LP must have a basic feasible solution if it's feasible. And because an optimal solution must be a basic feasible solution, right? Therefore, if a standard form LP has an optimal solution, meaning has the finite optimal solution, then one of the optimal solutions or the optimal solution, if it has a unique one, must be a basic feasible solution. In other words, we only need to look at basic feasible solutions to find the optimal one. And because even if it has many or multiple optimal solutions, they are all optimal. So it suffices if we just find a basic feasible solution that is optimal. So in other words, we can look at the set of basic feasible solutions, all the extreme points, and select the one with the minimum objective cost. Okay. In other words, you already see that there is an algorithm here that we look at all the basic feasible solutions, all the extreme points, and find one with the minimum cost. So that will solve linear program. This is why basic feasible solution is so important for linear programming. Okay, let's summarize. We learned that not every polyhedron has the extreme point, and not every LP has a basic feasible solution. And we exactly give the condition when a polyhedron does have an extreme point. Okay. But a feasible standard form LP always has at least one basic feasible solution. And if an LP has an optimal solution, that's finite, then one of the basic feasible solutions is optimal. All right, that is this part of the algebraic aspect of linear programming. And from next lecture, we'll start to talk about algorithm using all this geometric and algebraic understanding of linear programming to solve LP. Thank you.